Healthy trees start below ground. When arborists diagnose declining trees, manage urban landscapes, or prescribe treatments, the real story is almost always happening in the soil. Roots interact with soil structure, microorganisms, nutrients, water, and chemistry all at the same time. Understanding soil treatment is one of the most practical and tested knowledge areas on the BCMA exam. Today, we're going to explore how arborists evaluate soils, diagnose nutrient issues, and apply treatments such as fertilization, soil amendments, and aeration. And as you'll see, good soil treatment isn't about simply adding fertilizer, it's about understanding the soil system. In this chapter, we'll explore how soil properties influence tree health and how arborists improve soils through treatments. We'll examine how to interpret soil analysis and foliar analysis results. We'll look at nutrient dynamics, including macronutrient and micronutrient requirements, and how deficiencies develop. Then we'll explore soil management techniques such as aeration, fertilization, mulching, and soil amendment strategies. Finally, we'll discuss application methods, including surface application, subsurface application, injection, and soil drench application. These concepts help arborists diagnose problems, prescribe treatments, and restore soil function in urban environments where soils are often heavily altered. Guided concept walkthrough. Let's start with soil evaluation. Before prescribing any soil treatment, arborists should perform a soil analysis. This laboratory test measures nutrient levels, pH, organic matter, and other chemical characteristics. Sometimes a foliar analysis is also performed. In this case, leaf tissue is analyzed to determine nutrient concentrations inside the tree itself. When you combine soil analysis with foliar analysis, you can determine whether a tree is experiencing a nutrient deficiency or if a nutrient limitation exists due to environmental conditions. This distinction matters. A nutrient deficiency means the nutrient is absent or insufficient in the soil. A nutrient limitation means the nutrient may be present, but the tree cannot absorb it due to soil conditions such as pH, compaction, or poor root development. A common example is chlorosis, where leaves turn yellow due to insufficient chlorophyll production. Often this occurs when iron is present in the soil, but unavailable because the soil is alkaline. This brings us to soil chemistry. Soil reaction refers to the acidity or alkalinity of soil. When soils become alkaline, nutrient availability changes. Alkalinity describes the soil's ability to neutralize acids, which is different from simply being alkaline. Some soils also have strong buffering capacity, meaning they resist changes in pH even when amendments are applied. This is important for arborists. Attempting to adjust pH in soils with high buffering capacity can be extremely difficult. Soil structure and physical properties also influence root health. Soil texture refers to the proportion of sand, silt, and clay particles. Soil structure refers to how those particles aggregate into stable units that influence water movement and root penetration. Another critical measurement is soil bulk density, sometimes abbreviated SBD. Soil bulk density describes how compacted a soil is by measuring the mass of soil per unit volume. High bulk density usually indicates soil compaction, which restricts root growth and reduces oxygen availability. Soil compaction is extremely common in urban landscapes due to construction activity, foot traffic, and heavy equipment. Compacted soils reduce pore space, which limits water infiltration, gas exchange, and root expansion. Arborists may measure soil density using a soil probe or collect samples with a soil auger to examine soil horizons and evaluate the soil profile. A soil horizon refers to the different layers of soil that develop over time, such as the organic layer, topsoil, and subsoil. Understanding the soil profile helps arborists diagnose root limitations and identify where soil treatments may be most effective. Now let's shift toward nutrients. Trees require a variety of essential elements to grow and maintain their structural cells. These elements are typically divided into macronutrients and micronutrients. Macronutrients are needed in larger quantities and include nitrogen, phosphorus, and potassium. These are commonly called the primary elements. Trees also require secondary nutrients such as calcium, magnesium, and sulfur. Micronutrients like iron, manganese, zinc, copper, and boron are required in smaller amounts, but are still essential. All of these elements exist in the soil as minerals or dissolved ions that trees absorb through their roots. The ability of soil to hold nutrient ions is described by cation exchange capacity, or CEC. Soils with higher CEC can hold more nutrients and make them available to plants. Organic matter greatly increases CEC. This is one reason soil organic matter, often abbreviated SOM, is so important for soil fertility. Organic matter supports the soil food web, a community of microorganisms including bacteria, fungi, and other organisms that help break down materials and cycle nutrients. Mycorrhizae are a critical component of this system. These symbiotic fungi attach to tree roots and improve nutrient and water absorption. Some arborists apply soil inoculant products to introduce beneficial microbes or mycorrhizae into disturbed soils. Now let's talk about fertilizers. Fertilization is the process of supplying nutrients to plants. A fertilizer is simply a material applied to soil or plants to provide nutrients. Fertilizers can be inorganic fertilizer or organic fertilizer products. Inorganic fertilizers are typically manufactured mineral salts. Organic fertilizers come from natural materials such as composted plant or animal products. The fertilizer analysis printed on fertilizer bags shows the percentage of nitrogen, phosphorus, and potassium. This is often written as the fertilizer ratio, such as October 10th, 10. A complete fertilizer contains all three primary nutrients. Different fertilizers release nutrients at different rates. Quick-release fertilizer dissolves rapidly and provides nutrients immediately. Slow-release fertilizer and controlled-release fertilizer products release nutrients gradually over time. Some products also contain water-insoluble nitrogen, abbreviated WN, which slows nitrogen availability. Another category is slowly soluble fertilizer, which dissolves gradually as soil moisture interacts with the product. These controlled nutrient release patterns help prevent nutrient loss through leaching. Leaching occurs when water moves soluble nutrients downward through the soil profile beyond the root zone. A related issue is volatilization, where nitrogen compounds convert to gas and escape into the atmosphere. This often occurs when fertilizers are left on the soil surface under warm conditions. Another concept to know for the BCMA exam is salt index. The salt index measures the potential of fertilizer to increase soil salinity. High salt levels can damage roots and cause fertilizer burn, where salts draw water out of root tissues. This becomes particularly problematic in saline soils. Saline soils contain excessive soluble salts. Saline Sodic soils contain both salts and sodium. Sodic soils contain high levels of sodium that disrupt soil structure. In Sodic soils, clay particles disperse, destroying soil structure and limiting water infiltration. Arborists may evaluate sodium levels using the sodium absorption ratio, or SAR. In some cases, gypsum is applied as a soil amendment to help displace sodium and improve soil structure. Field-based arborist examples. Imagine you're inspecting a street tree planted in a narrow tree lawn. The leaves are pale yellow. A soil analysis reveals adequate iron levels, but the soil reaction is highly alkaline. This suggests the chlorosis is caused by nutrient limitation rather than true nutrient deficiency. In this situation, arborists might apply chelates, which bind to iron and keep it soluble so the tree can absorb it. Now imagine another situation. A construction project has heavily compacted soil around mature trees. The soil bulk density is extremely high. Water pools at the surface after rain. In this case, arborists may recommend aeration to relieve soil compaction and improve oxygen movement. Aeration may involve vertical mulching or other subsurface techniques that break up dense soil layers. Diagnostic thinking for arborists. When diagnosing soil-related tree decline, arborists should consider several factors. Start by evaluating soil structure, soil texture, and soil organic matter. Look at the soil horizons and overall soil profile. Ask whether soil compaction or poor drainage is restricting root growth. Then, evaluate soil chemistry. Is the soil reaction acidic or alkaline? Are nutrients present but unavailable? Are salinity issues affecting root health? These diagnostic steps help arborists determine whether to apply fertilizer, adjust soil chemistry, or focus on improving soil structure. Exam Insight Moment. A common BCMA exam concept is distinguishing between nutrient deficiency and nutrient limitation. Another frequent question involves recognizing how soil pH affects nutrient availability. Understanding CEC, soil organic matter, and nutrient cycling is also essential. Let's briefly connect the key ideas. Healthy soil contains balanced soil texture, stable soil structure, and adequate soil organic matter. These properties support the soil food web and mycorrhizae that help trees acquire nutrients. Arborists diagnose soil problems using soil analysis and foliar analysis. They then apply treatments such as fertilization, soil amendment strategies, or aeration to restore soil function. Summary. Soil treatment is one of the most powerful tools arborists have for improving tree health. But effective soil treatment requires understanding soil chemistry, soil physics, and nutrient biology all working together. In the next chapter, we'll shift from soil treatments to structural support systems, exploring cabling, bracing, guying, and lightning protection used to stabilize trees and reduce failure risk. Because when you truly understand the soil beneath a tree, you gain the ability to manage the entire ecosystem supporting it.
Thanks for listening to the Arborist podcast. Let's keep building your arborist knowledge one domain at a time. If you found this useful, please like and subscribe.